In the last two videos, we looked at the graphs of secant and cosecant. I want to now take a look at transformations of those functions. So I've got here f of x is 3 cosecant of negative 2x plus 1. That's a transformation of the cosecant graph. And my directions are pretty standard. Graph exactly one period, make sure I start and end at an asymptote, and label the important points. Well, the way I'm going to graph a transformation of secant or cosecant is going to be in two steps. I'm going to first graph the corresponding transformation of sine. Okay. Now I'm choosing sine because this is cosecant, which is the reciprocal. If I were doing a transformation of secant, I would start with the corresponding transformation of cosine. So that would be y equals 3 sine of negative 2x plus 1. Okay. So I'm going to graph that first. Once I have that, I'm going to draw in the asymptotes and flip the bumps. Now, the reason that's going to work is because if I think in terms of the horizontal transformations here, I'm doing the same horizontal transformation to sine here that I'm doing to cosecant here. That's going to change the locations of the zeros of the sine function. But where sine is 0 is exactly where cosecant has an asymptote. So if I transform the sine graph and look at where it would be 0, that's going to tell me where cosecant will have an asymptote. Okay. The vertical transformations, I'm going to wait until we've actually drawn the graph and then address why it works to do the transformations for sine and then flip the bumps, and that gives us the transformations for cosecant. So I will return to answering that question. All right, so if I want to graph this, first thing I'm going to notice is, ooh, there's a negative in there. Now this was sine. Sine is an odd function. Opposite input gives me the opposite output. So this is the same as negative 3 sine of 2x plus 1. Okay, excellent. Now, what I'm plugging into sine, that multiplication by 2 is going to affect a horizontal transformation. The multiplication by negative 3 and the adding 1, we're doing that after we evaluate sine, so that's going to give me vertical transformations. Okay, so let's see. Let's just keep track of the important points that we get with the vertical transformation. So prior to transformations, we would have 1, 0, and negative 1. We multiply by negative 3. Remember, vertical transformations respect the order of operations. So we do the multiplication first and then the addition. So when we multiply by negative 3, 1 times negative 3 becomes negative 3. 0 stays 0. Negative 1 goes to 3. And we've done a flip. So with the regular sine graph, we would start in the middle going up. Now we're going to start in the middle and go down. Okay, then we add 1. So this was multiplying by negative 3. Adding 1, we get 4, 1, and negative 2. So those are the y values that we will care about. Let's figure out the x values. Now I know that sine will go through one complete cycle as the input varies from 0 to 2 pi. Well, the input is 2x. So I put that in the middle and I solve for x. So we divide through by 2. And we get 0 less than or equal to x less than or equal to pi. Okay. So that tells me that my new period is pi. Okay. Now I can double check. Pi minus 0 would be my ending point minus my starting point. That's pi. That's also equivalent to 2 pi, the original period, divided by this number that we're multiplying by. Okay. So that's equal to 2 pi over 2, and it's also equal to pi minus 0. So it checks. Okay. That means that the increment is going to be that new period divided by 4. And so that's going to mean that the x values that we care about, let's see, the x values that we care about are going to be, we start at 0, and then we'll have plus pi over 4. And then we hit 2 pi over 4, but I can see that will reduce to pi over 2. And then 3 pi over 4, and then 4 pi over 4, but that would reduce to pi. And that is supposed to be my ending point. I'm liking it. Okay, so I think we're ready to draw our helper graph of the transformed sine function. Remember to draw it as a dotted curve. You can place bets on whether I'm going to remember or not. We'll see. I'll go back and fix it if I draw it as a solid. So I'm going to mark off my x values. 0, pi over 4, pi over 2, 3 pi over 4, and pi. The y values that we care about, we've determined are -2, 1, and 4. And I like to just draw in dotted lines at those heights. Okay. And then, let's see. This is a sine function, but it's flipped. Oh, let's record that. So we're starting in the middle, but going down. So we'll be at a middle value here. At pi over 4, we're down at -2. At pi over 2, we're back at the middle value of 1. 3 pi over 4, we're at 4. And then at pi, we're back at 1. Oh, I'm going to remember to draw it as a dotted curve. So there's one period of the sine function. Now, one thing that's very important, notice what we're graphing here with this dotted curve is 3 sine of -2x plus 1. I'm not concerned with where this graph is 0. I'm not concerned with those places right there. I mean, if I had added, instead of adding 1, if I had added 5, this graph would never be 0. What I'm concerned with is where sine was 0. And I would evaluate the sine before I did the multiplication by, I'm sorry, this was -3. The multiplication by -3 and the adding 1. Okay. Now, 0 times -3 is still 0, but adding 1, it moved up to this middle value. So the asymptotes are where sine was 0, which is where the transformed graph is at this middle value, even if that middle value isn't 0 anymore. So if there's a vertical translation, you're not looking for where your graph crosses the x-axis. You're looking for where it crosses that middle value. So my cosecant graph will have an asymptote along the y-axis. It will have an asymptote at pi over 2, and it will have an asymptote at pi. Okay. Now, that no longer neatly divides things into places where the y values on this graph are positive or negative, but it does divide things into places where the y values of sine would be positive or negative. Because again, we evaluated sine, and then we did the vertical transformations. Okay? All right, so now all we have to do is flip the bumps. I think I need to clean up my board so that I've got some room for that. So notice we've got the bump that opens downward first, and then the one that opens upward. Now in this one it was kind of nice because our starting point was the location of an asymptote, so we didn't need to adjust. That worked out kind of nicely. But I did want to point out that the asymptotes are where sine is 0, which is where the transformed graph is at whatever the middle y value happens to be. I promised I'd come back and talk about why doing the vertical transformations for sine worked for doing the vertical transformations for this cosecant graph. Because it's a slightly different explanation than what we have with the basic graphs. With the basic graphs, we had a high point of 1, and we said, oh, we're just taking the reciprocal, and the reciprocal of 1 is 1. And we had a low point of -1, and the reciprocal of -1 was 1. Here, I'm not taking the reciprocal of this graph, because the reciprocal part is in the cosecant. I'm taking the reciprocal of sine of -2x, but I'm doing that before I do the multiplication by 3 and the adding 1. So I'm not taking the reciprocal of 4. And if I were, I'd be doing it pretty badly, because the reciprocal of 4 is not 4. It would be 1/4. Okay? So here, this flipping the bumps doesn't quite correspond to taking the reciprocal of what I have. But if I take a look, these were the original high and low values of sine. And what I did is I tracked where they went. Okay? Now, I did that by looking at the vertical transformations that we were doing. But I'm essentially doing the same vertical transformations here. Now, with the sine, I used the fact that sine was odd to put that negative on the outside. Can we do that here? Can we say this is -3 cosecant of 2x plus 1? The answer is yes, we can. Because if sine is odd, its reciprocal will also be odd. Because if the opposite input to sine gives me the opposite output input to cosecant will give me the reciprocal of the opposite. So I can do that as well. So while I was thinking of this as this was the high, middle, and low value for sine, if I ignore the 0, this was the low point of the upward opening u, and this was the high point of the upward opening u that I got when I graphed cosecant. And now I'm doing exactly the same vertical transformations to that. We're going to multiply those y values by -3, so the 1 becomes a -3. And then we're going to add 1, so it becomes a -2. Okay. So we did the flip, the stretch, and the shift up. So keeping track of the high and low values for sine are going to keep track of these turning points for cosecant. So you can go ahead and just transform, in this case, the sine graph, and if you're doing a transformation of secant, you would transform the corresponding cosine graph. Kind of a neat trick. Okay. So I'm going to have you folks try one, and again, because these problems are time consuming, I want you to be able to get a head start on your homework. So I've selected problem number 15 from the homework. So you're sketching y equals secant of -x minus pi over 4 minus 2. So you're going to use the fact that secant is the reciprocal of cosine, sketch me the corresponding transformation of cosine, then draw in your asymptotes and flip your bumps. We'll go over it in the next video.